Hello, everyone. Thanks for joining us today. My name is Charles Rice. I'm the host for today's webinar, SimCenter Test Lab CAN bus acquisition. And your presenter for today is Pete Shelderbrand. Pete is an application engineer for the Siemens SimCenter Test Lab products. And as always, during the webinar, if you have any questions, please type them in the questions panel in your webinar control area, and we'll type a reply to your question there, or maybe even sometimes answer the question live during the webinar. We'll follow up with you later. Well, now that we got that out of the way, well, why don't we pass it to Pete?
Well, thank you, Charles. And by the way, when you type in questions, if they're very difficult ones, make sure they're directed at Charles. It's just my personal preference. As Charles said today, the topic is CAN bus data acquisition. So if you're a SimCenter Test Lab user using our SCADAS, you might try and acquire data from a controller area network. Thought I'd spend a few minutes maybe to explain exactly how CAN bus came about and what it is. Back in the day, when I first started my career with Siemens in 1986 or so, vehicles were becoming more and more electronic, meaning they had more and more electronic controls. So when you went to start up your car, the electronic control system would do things to make sure you didn't flood your carburetor, things like that. They got smart. So they had embedded sensors, and they communicated to each other over analog wires, things like the engine to the transmission. And one of the things that was happening is there was a need for more and more electrical controls. And so these wiring harnesses were becoming bigger and heavier. And they were even like the weak point of a lot of cars. Like if you one of these wiring connections went bad, then your car didn't work. So that was becoming a problem. And they're also getting heavier, which would have a penalty for fuel economy. So the supplier, Robert Bosch, developed a system where signals could share a common wire. And that's what a CAN bus system is, or a controller area network. It's a single wire, although technically it's actually two wires. But the idea is that multiple signals share the same wire, and they're digital signals. So they kind of have like, even like how the internet works today, they have a address on them so that they get routed to where they're intended. You can think of it as like a postal system, right? Like, so the transmission might need to let the instrument cluster know what gear it's in, but also has to let the engine know. So these packets of information get sent back and forth over this common wire. And today's cars, instead of just a few, dozens of things communicating, you literally have thousands of electronic components all communicating with each other. So over time, this thing has only grown. And there's some terms, I guess, to know about, things like electronic control units. These are the things that are embedded in each component on your car that are doing this communication. So we have electronic control units, we have embedded sensors, they're all passing information back and forth. And just for reference, here are some of those different terms that you might see throughout the presentation. CAN is just one type of network. So there's things like a LIN, which is also a network that you typically have in modern vehicles. And those are used for slower speed communications, like the door locks, the infotainment center, things like that. And then there's terms like onboard diagnostics, or OBD, that you might hear. That's really separate than CAN. These are typically things that are used at the dealership to diagnose what's going on. So it's a slightly different protocol, but it sometimes is carried over the same wiring connection. And it's also typically used for things like emissions. Hopefully that makes a little bit of sense. CAN bus, there is an ISO standard, 11898 is most common. And also for heavy trucks, off-highway equipment, bulldozers, and things like that, there's the SAE J1939 standard that dictates how this communication is done through a CAN bus. Maybe point out a few practical things. If you're on a motor vehicle, one of the ways you would access CAN bus typically is underneath your steering wheel on the dashboard. So on the left-hand side underneath, you typically find this onboard diagnostics port. A lot of times that is also connected to the CAN network. So that's an OBD connector. And it can be a bit confusing because on one vehicle, you might access the CAN through this OBD connector. But because this is actually done for emissions, sometimes the CAN bus information is not available on that connector, might be somewhere else. You have to look in the owner's manual, etc. This is an OBD style connector. That's not technically what CAN uses. CAN uses a serial port with 9 pins, and it doesn't necessarily use all of them, but it's defined on this 9-pin standard. So you would typically need to read CAN bus through an OBD port. You need a converter cable that goes from OBD to this 9-pin CAN bus, and that's the type of connector that you typically see on a SimCenter SCADAS. We provide some sort of wire to go to this 9-pin connector to read CAN bus. If you're going to read CAN, that's how you would physically connect up, but then you might need, you need a decoder ring, if you will, and that's typically contained in a file that's called a DBC file. Somewhere I have the definition, database CAN or something to that effect. And this DBC file contains information about each one of these electronic control modules or electronic control units that we were talking about, what signals are present and how to decode it and how to read it. So this file, in fact, is an ASCII file. You can open it in Notepad or whatever you want to open it in, and you can see it'll list for a given vehicle all that information. You'll find, like, for example, for the odometer, there's some signals that come in and out, like, how far the distance that we've rolled and the vehicle speed and a bunch of things. These are all the signals that are coming in and out of the odometer component. Whereas the engine might have a different list of signals coming in and out of it, that electronic control module for the engine. So the DBC file literally lists all the signals that are being communicated over the CAN. And they're specific to a particular vehicle and to a particular powertrain configuration. You can imagine if you have a vehicle with more than one powertrain, like a 4-cylinder and a 8-cylinder, this file is different because there might be different information that needs to be communicated for that vehicle. And normally these DVC files are something that the manufacturer of the car uses themselves. So it's not something that's generally available that you can go on the internet and download for any given car, because it really contains a lot of the information and signals that are traveling back and forth in a car. I'm going to just show briefly how you might set up and use the DBC file once you've connected up inside the test lab.
Go to the channel setup page and select in the upper right the CAN settings menu. There you can select the DBC file that contains the information about the particular vehicle and powertrain that you're using. You can set the baud rate, usually 500,000. You'd also pick the device that you're using. This would be, for example, if you have a CAN card in your SCADAS Mobile, or if you're using Access built-in CAN. And then you can view the CAN channels in the overview here. By default, in a CAN bus file, you'll find many channels. In this case, this particular file has over 1,000 channels. If I was interested in just the engine RPM, I could type in RPM and then do a search for just the RPM channels. Then I would select the engine RPM channel, I'd hit apply, and now I have this channel active. If I go back to channel setup, you see it here. I'm also going to save the raw CAN files if there's other CAN channels I want to decode later. Instead of using the default name, which is a bit long, I can come in and say something like CAN engine RPM. And once you have your CAN channel set up, you can go to the measure worksheet to view it. Here, I can open the Data Explorer and I can drop in the CAN channels that I want to see. For example, I can look at the CAN channel in RPM, and I can also look at it versus time. I can also look at my data channels at the same time. So my CAN channels and analog channels will be recorded together. And now I can turn on my car and you can see the engine RPM updating. And as I press the gas, you can see the RPM changes. And that is how you record CAN channels plus analog channels all in one acquisition.
Okay, so hopefully that made sense, Charles.
Yeah, well done.
All right, so what I did there was I recorded the RPM along with my analog channels. So pretty straightforward. One of the things about these digital signals, unlike an analog signal, is if you have problems, because it's digital, it's like an all or nothing. If I don't see the engine RPM, if it's just reading zero, it's not like you can go in and fiddle with a tachometer. You got to go and maybe have the wrong DBC file or something like that. You have to kind of figure it out digitally, if you will. Now, this option that I had highlighted earlier, where you have the save raw data, I just want to point out when you have that checkbox on, and you go and you look inside TestLab and you look at your throughput file, you'll see the regular throughput file with all the analog channels, your strains and accelerations. It'll also have all the CAN bus files you monitored online in there. But in parallel to that, you'll also find this digital bus data. That file indicates that you have the raw CAN data. So maybe after you've done the recording, you're like, I needed more than engine RPM. I needed something else. Well, if that's the case, you can take the same DBC file. Maybe you didn't even have the DBC file, so you have the raw CAN file. And then you can go in, select the DBC file again, and then you can select which channels out of the CAN file you want to process and decode. So that's what that does. And you do the decoding of a raw CAN file inside the time data selection worksheet inside TestLab. Okay? You might be wondering, how close is the data I get from CAN and how well does it match up to the actual vehicle speed if I measured it with a tach or I measured it with a GPS? We overlaid all three here. We have the GPS vehicle speed, we have the vehicle speed from a tachometer and from a tach, and you can see that they all overlay very, very close. So that's the good thing about using something like the CAN. It has a pretty good update rate, and we can get good RPM and engine information. I'll elaborate on that a little bit more later on, but I also wanted to mention this CAN, the idea of simplifying the wirings, sharing multiple signals over a single bus, doesn't just apply to vehicles. There are a lot of sensors which are made now which also have CAN outputs. If you are using something like a wheel force transducer, a lot of these have CAN outputs. There's 6 signals, and if you're on a regular car, you have 4 wheels, so you have 24 analog channels. And normally you would have to use 24 analog channels to get the forces and the moments and everything else from a wheel force transducer. A lot of them have a CAN output now, and then you can plug really with the data rates, because CAN is a bit limited compared to like a SCADAS and a full analog signal. You have 2 CAN inputs. You can take 12 channels on each and simplify a wheel force transducer down to 2 wires through CAN. At Siemens, we also sell something called a TCK8 thermocouple card, which is CAN bus based, and that will plug in the CAN. And the idea is, instead of using something like a T8 card, which takes up 1 slot, that'll save you from filling up a slot. You can use the built-in CAN on your SCADAS and not take up valuable data acquisition slots. So that allows you to put more channels into your data acquisition unit. That make sense to you, Charles?
Yeah, that's pretty handy, that TCK8.
Yeah, and there's a lot of different sensors out there that are CAN bus based, but I also want to point out, you'll sometimes hear the term CAN open or CAN open transducers. Well, this is not quite the same thing. CAN open is a standard that was developed to exchange information between different bus networks. And there's this thing called an OSI, Open System Interconnection Model, for how I'm going to get my CAN to talk to some other digital bus or whatever. Defines a bunch of things. Only 2 layers or 2 sections of that standard deal with the actual CAN communication. That's the physical connection and this DBC file. So just because you're using the CAN open standard, well, that doesn't necessarily mean that the CAN part of that follows. And actually within here, there's different implementations of CAN. Some don't use a DBC file. So at the end of the day, if you hear, okay, I got some transducers that are CAN open, will they hook up to my SimCenter SCADAS? The answer is only if they have a DBC file and they go over the standard 9-pin SCADAS, 9-pin CAN bus connection. So CAN open does not guarantee it works with your SCADAS. And really, it's not even aimed at making sure it works. It's thinking about this whole interbus communication. So just thought I'd mention that. And in fact, I was going to even point out some more standards and other things that you might hear. So you hear the term CAN bus, J1939, 11898. About 100 updates per second on a channel you can get, maybe even more, depending on exactly how many channels you have coming through on the CAN bus. It's fairly fast, not as fast, obviously, as 100,000 samples per second, like a SCADAS can do. But the need came, more and more electronic sensors embedded inside products. And so there's a higher throughput rate needed to communicate between these different electronic control units. And CAN bus was reaching its throughput limit. No more messages could be crowded in. So there's a next generation CAN bus called CAN FD. And now CAN FD stands for Flexible Data Rate, the FD part, Flexible Data Rate. It's faster, allows more communication, does not use a DBC file, uses this AUTOSAR file. If you're using one of our systems, you also have to make sure you have the appropriate hardware. So on the SCADAS units, you can upgrade to a CAN FD interface, which handles both CAN FD and CAN bus. The original hardware was CAN bus only. Now you can get a CAN FD plus CAN bus compatible. Different file required, files for a higher rate. Pretty common now. Many vehicle manufacturers are switching from CAN bus to CAN FD. As I mentioned before, there is this standard called LIN, which is low speed and a bit cheaper, or like on the infotainment side. We don't support that directly. You would need a translator box between the LIN network and the CAN bus input on your SCADAS in order to read that. And also to point out, something we do support is a standard called FlexRay. This FlexRay was really one of the first attempts to go for a higher speed bus, and it had a new ISO standard, much higher speeds, which is kind of cool. And you do find this on some vehicles, high-end German luxury cars typically, and they use a FIBEX file. It didn't really catch on. It did come out before CAN FD did. The reason it didn't catch on, it was just quite a bit more expensive than CAN bus. So the price of CAN FD components, you can actually use some of the components used for CAN bus, was relatively cheaper, thus making it more popular because the cost wasn't as much, but you're getting more data through it. So FlexRay, higher speed, again, that requires a special card from our side if you're going to use it for for this high speed stuff. Another type of bus or thing you'll hear is this OBD2, which also has an ISO standard. It's required by legislation to be on gasoline engine cars for emissions testing. And I was going to explain a little bit about that. It's because it's kind of interesting. You have your engine RPM. The nice thing about this is OBD2 broadcasts engine RPM as well. So I could get my engine RPM out of my vehicle, and because it's standardized for emissions, I do not need a specific DBC file to do that. And there are about 80 other signals that are available over OBD that are legislated for emissions testing. So I don't get 1,400 signals like I would with CAN if I had a DVC file, but using this OBD approach, I can get 80 legislated signals. They tend to be slower speed, so they're not as fast as CAN, but I'll show you they're still pretty good. Just a warning, only on newer vehicles over the last 5-6 years do you find these all available standard. Before that, it was kind of hit and miss a bit to get the standardized signals. Certainly, if you hook up to a 1980 Oldsmobile, you're not going to find these legislated signals. Fortunately, I haven't updated my car since then. So, but when I do, I'm going to have a lot of electronic signals. So an OBD file, the way it's supported in TestLab, we provide OBD DBC files, and it's a little bit confusing because really OBD2 is a different protocol than CAN, but we still use the same interface in our software. And we provide some pre-made DBC files that have these standardized signals in them so that you can grab engine RPM, vehicle speed, things like that. I don't know why you need vehicle speed for emissions testing. I guess maybe if they put it on a dyno or whatever, it gives you air temperature and other things. These signals, these OBD2 signals, are not broadcast by default. So what that means is that I'll even go up here and show a little bit of this. It means that instead of passive here, because on a CAN network, all these signals are automatically broadcast between these electric control units, right? Because they have to be for the vehicle to run. The emission signals are not there on the bus by default. So you have to request them. So that means this CAN acknowledge mode has to switch from passive to active. And if you've selected the right OBD file, then you will be able to get these signals. It operates exactly the same as CAN. It has a limited number of signals. One of the things that is handy, I'll go back to the slides and show this, is we have a little setting here called sample and hold versus linear. And you can set linear or sample and hold on these things. Because there's a slower update rate on these OBD2 signals, it's sometimes nice to use this linear. Let me see if I can show you why exactly. So if you look at a digital signal close up, like one that comes from the OBD, you would see this little stair-step effect because it's broadcasting discrete steps. And when you switch this to linear, we actually make a nice smooth line that follows the data points that are coming out of this. And we find that can represent the RPM very well. So this shows OBD2 versus a physical tach, and you can see they match very well using that linear interpolation. So that feature is in the software to help you see this a bit better. Do you think the audience has any questions at this point, Charles, or are they, maybe asleep at this point?
We don't have any questions. We might be wanting to know what car you're going to upgrade to next, though.
Yeah. Well, if I was to upgrade to an electronic or electric vehicle, maybe a little bit of a sad thing. This OBD2, which was developed for emissions, guess what, Charles?
Oh no! Don't tell me.
Yeah, it will not work on an electric vehicle. It's pure electric. So that's something to keep in mind. You lose those legislated signals when you go to an electric vehicle. Okay. I thought I'd point out then one other thing here. That is something called CCP or XCP. It's from ISO 22000. The other kind of interesting thing is, we're talking about communication between these electronic control units. So these are things that have to be broadcast for, the transmission has to talk to the engine, etc. But there are actually a lot of signals, too, that never get broadcast. They're known internally in this module, or subsystem of the car, the engine or the transmission, but that information does not need to be broadcast. So in that case, that's where CCP comes in. That'll allow you, this is called CAN bus calibration protocol or generic calibration protocol for certain electronic control units that are made a special way. this will allow you to access those signals that exist only inside the component. So let's take the example of a transmission. For example, the engine needs to know what gear the transmission is in, needs to know the input speed to the transmission. It needs to know the output speed, right? But it probably doesn't need to know what's going on inside that transmission. So some things we're not going to transmit to the engine. Things like whether the clutch is slipping or not. There's a whole bunch of shafts in here, or different gear ratios and things. It doesn't need to know the intermediate shaft speeds as the engine. It only needs to know what's coming in and out, the shift fork drum position, a lot of other things. Yet, if you're developing a transmission, you might want to know all those things and be able to record them along with your analog signals, especially if you have a car that's maybe lurching or doing some erratic stuff. So to do that, it's pretty simple. I'm going to draw a box because I realized I left the slide. I got my SCADAS, and the SCADAS can only read CAN bus. So it expects a CAN signal, not a CCP signal. We have the vehicle over here, and so what we need in between, and they're very common devices, we need a gateway device. A few companies make those, and feel free to contact Charles after, and we can recommend some. That takes the CCP out here, and then translates that CCP into a CAN signal for the SCADAS. So a small device can sit there, act as an intermediary to get that information to the SCADAS, where all your analog signals from the vehicle are also coming in and then can be coordinated together. So hopefully that made sense. I just wanted to, with the presentation, our intention was to give you an overview of these different protocols so you know what they all mean as you try and translate those signals, and give you an idea of how to set that up in the SimCenter Test Lab software and with a SCADAS.
Thank you, Pete, for the excellent presentation and overview of CAN bus acquisition with SimCenter Test Lab. Please don't hesitate to email me or Pete, and we'll get you an answer. Have a great day, and hope to see you at another webinar in the future.